welcome everyone. Welcome to our session on autoencoders. So in today's session, we are going to understand about how we can make use of autoencoders in development of applications like image denoising. In our previous session, we have already worked on development of autoencoders. So we have designed a simple autoencoder in the first session, followed by we have been working on different types of autoencoders. Like we have worked on deep autoencoders, along with we have also worked on prediction using deep autoencoders, which we have done in the previous session. We have also explored convolution autoencoders, which are used in practical cases. So you have got to know about convolutional 2D classes. You have got to know downsampling and upsampling. And yesterday I have asked you to train convolutional autoencoder. And once the training is completed, you have to check the output. So the output, you can see that the loss on the testing data set was approximately 0.095. So that's a good accuracy, which we have accomplished. Followed by what you need to do, you need to decode, you need to predict using the autoencoder for the test set. And finally, you have to plot the images, which has been generated using convolutional autoencoder. So here how we have got an autoencoder here. Now what next we need to do? Now we'll continue from here, and we are going to make use of an application of autoencoders. Okay, so let's get started with applications of autoencoders. And one such applications which is mostly used in the industry is image denoising application. Okay, so let's say if you have a noisy image available and you have to extract the important features or important information out of it, that's something we are going to implement. So let's say I'm going to show you certain images, what exactly we'll be doing in. Let's just call as noisy image. Let's say we'll search for the MNIST dataset also. Noisy image MNIST. So here we have got a nice image. Okay, so guys, you can see, suppose we have got an image somewhat like that. This could be a better example. So now on the right hand side, you can see that there are two images displayed, and these images are the first image at the top is a noisy image. So you can see that there are a lot of noises in the background of these images, but using the concepts of autoencoders, using the concept of artificial intelligence, we can actually extract the information from the noisy images also. Okay, so this is what something which is an application of autoencoder, which we are going to implement today. So let's get started how we are going to implement image denoising based autoencoders. Let's go for it. So we'll be continuing with our previous script, which I have been using. And if you want, let me just share the script with all of you. Here we go. Is my voice audible to everyone properly? And I'm sharing a script with everyone. So this is my script, which we have been working on. We'll be continuing from here. If you want, you can run all the cells and you can continue with me on the script here. Now let's see. So we'll be working on applications of autoencoders. So we have developed this convolutional autoencoder, whose output you can see here, whose value loss, which was the loss over the testing data set, was 0.095. So now we will be using our convolutional autoencoder to work on image denoising problems. So how we are going to proceed with that? We will train the autoencoder to map noisy digit images into the clean digit images. That's what we are going to implement. So first of all, what do we need to do is we need to have certain noisy digits. And in order to create noisy digits, what we can do, we can make use of Gaussian units to create a noise matrix. And then we can clip the information between 0 and 1 so as to grab that noise. And then we can generate the noisy images. So let's have a look. So the first attempt would be to generate some noisy images. And then using those noisy images, we will be predicting the actual images. Okay, let's get started. So we are going to import from keras data sets. We're going to import MNIST, which is required. Let's just run this cell. We also need to import numpy because we could be using various operations on numpy like random normalization, which you will be using today because you have to generate noisy images. So let's import numpy, import numpy as np. Okay. Now what you're going to do? Let's load the data set mnist dot load data. Okay, and again we are going to save that into the X training and the X testing. Okay, so once we have got the data ready, next what we are going to do, we're going to reshape the data for 3 dimensions using channels first, using channels last. In fact, I've already told you about what is channel last. You have already understood that yesterday. So we are going to make use of xtrain.astype, and we are going to make use of float 32. We're going to divide that with 255. Let's save that into xtraining again. Okay. Now, once you have got the training information, let's just grab the testing information as well. As type float 32 divided by 255 and save that into xtest. Okay. We are going to get xtrain and xtest. Let me just run that. Now we have got the data set downloaded for MNIST. In the next cell, what we are going to do? Now let's create the 3-dimensional images from the input data set. So for that, we'll be using NumPy. We're going to reshape the content. In order to reshape the content, we'll be using the training information. And along with the training information, we are going to pass the length of the number of elements available in X training data. And we are going to convert that into 28 cross 28 cross 1. So it's already 28 cross 28 information is already available, but we will be adding the channel information, and that will be added at the last. So we are going to get a 3-dimensional X-trained data set using channels last. Along with that, we are going to use np.reshape. We are going to make use of xtest again. Using xtest, we are going to get the length of the xtest, and we are going to convert that into 28 cross 28 cross 1. So that we are going to grab xtest data of 3 dimensions as well. Now what next we are going to do? So here, your 3-dimensional images are available for training and for testing. Okay. Now, okay, what next we are going to do? So introduce some noise in the original data. Okay, तो हम कुछ noise generate करेंगे. Let's say 50% noise हमें generate करनी है. जो भी हमारी current images हैं, उसमें around 50% noise अभी हम add on करेंगे. You can change the percentage of the noise which you want to introduce. Initially, I just want to take 50% noise, कि हमारे पास आधा original data होगा, आधा noisy data है. In every individual image of the character in the MNIST. ये वाला gate बंद कर दीजिए. Gate बंद. Okay, noise factor 0.5. Now what next you are going to do? So let's generate the noise. To generate the noise, what we are going to do? We are going to make use of the training data. We are going to make use of the noise factor, and we are going to take a randomization from 0 to 1, depending on the number of elements available in the training. So for that, we'll be using NumPy. So what you can do, you can make use of NumPy randomization, and we are going to have a normal randomization. So what exactly normal dimension is? It actually draws random samples from a normal Gaussian distribution. This Gaussian distribution is very important for all of you. So kindly keep a note of it, that how we are making the Gaussian distribution. Gaussian distribution is nothing but it is actually displaying the metrics of a physical entity. ओके, सो सपोज आपके पास कोई एक स्पेसिफिक इमेज है, मान लो 28x28 पिक्सल की कोई एक इमेज है, तो वो इमेज आपके पास एक फिजिकल एंटिटी हो गई है, ठीक है। अब अगर आपसे मैं कहूँ कि ठीक है इसी साइज का कुछ और एक एलिमेंट बना दो, तो आप एक नॉर्मलाइज्ड गॉसियन डिस्ट्रीब्यूशन करेंगे फॉर द साइज ऑफ 28x28, लेट्स से, okay. So you can in fact read more about the Gaussian distributions here. We can quickly go here. Let's go to google.com and you can define Gaussian distribution. Okay. So what could be Gaussian distribution? Here we are taking the normal distribution. So let's have a look. What are we trying to do with the normal distribution? So it's nothing but, in probability theory, a normal Gaussian distribution is a type of continuous probability distribution for a real valued random variable. Okay. The general form of its probability density function is 1 upon sigma raised to the power 2 pi exponential raised to the power half of this is your x minus mean upon sigma, that is your mean value which we actually calculate depending on normal distribution and normal deviation. So mu is the mean as well as sigma is the standard deviation. So x minus mu upon sigma we generally use for scaling. Okay, so this is like distribution. Scale distribution you can always understand like let's say if you have a matrix of 28x28 and you want to display it on a range of 0 to 1, let's say. ओके, सो वहाँ पे हम एक स्पेसिफिक रेंज में रखने के लिए हम स्केल यूज करते हैं, बट अगर आपको उसको नॉर्मली डिस्ट्रीब्यूट करना है इंफॉर्मेशन को डिपेंडिंग ऑन द रियल वर्ल्ड रैंडमनेस जो भी अवेलेबल है, तो उसका जो स्पेसिफिक फंक्शन है दैट इज दिस. सो दिस सॉरी where is the annotations here? So this is the mathematical equation which is generally implemented when we normalize the Gaussian distribution. Okay. Gaussian distributions के कई सारे applications हैं which you can actually use here. Generally अभी जब हम आगे generate करेंगे कई सारे images को, तब भी आपको ये use करने पड़ेंगे normal distributions, ठीक है. So I would suggest कि आप लोग एक बार Gaussian normal distributions के बारे में mathematically पढ़ें, and that will generate a lot of information in your mind. Okay. Now let's see. So let's get back. We are going to perform a Gaussian normal distribution. So we will be implementing that equation here. So as I said, I would like to have a value starting from the location parameter. Let me just show you what all parameters this has. So the normal distribution actually contains an LOC value and a scale value. Okay. So this will start your starting point and up to what point you would like to scale and the size of the data which is available. Now, what would be the location? Location is the mean of the distribution. Okay. So arithmetic mean of the distribution should be 0. That means once you perform standard scaling, the value could be between -1 to 1. It could be -2 to 2. It could be -3 to 3. So in all these distributions, let's say, if I give you an example, let's say I would like to perform some normal distributions and I'm sharing some of the examples with you. Let's say we have a data. Let's say we have got a data of 28x28 pixels somehow. Okay, that's an image. And when I have normally distributed, I can normally distribute it to a range of 0, -1 to 1. And in this, if you can understand, the scale is equal to 1 here, and the scale is equal to 1 here, and the mean is equal to 0 here. Similarly, we can have any number of cases like -2 to 2. Here, as you all can understand, the scale is equal to 2 and your mean is equal to 0. So mean will always be 0 and scale you can set accordingly. And then your data will be normally distributed. So similarly, what am I going to do here? I will be taking the mean value as 0. Okay, I hope this is clear to all of you what exactly we are trying to do. We are trying to set, okay, we are trying to set the mean value. Let's say the mean value will start from 0.0, followed by we'll have a scale value, and I would like to scale it to 1.0. So this is I'm using for random distribution, random Gaussian distribution. Along with, we have to define the size also. So size for this parameter will be x underscore training. Okay, we're going to define x train dot shape of the inputs which you will be taking. Okay, I hope this is clear. So what we have got, we have took the training data, we have taken a 50% noise factor, and we have taken a normal random distribution values for the number of elements, for the number of rows and columns available in the training data. And we will be distributing the values with a mean value of 0.0 and with a scale value of 1.0. So this process is nothing but it's a standard scaling process. Okay. So using Gaussian distribution. So standard scaling you already understand. Whenever you represent any information on a scale of 0 to 1 or on a scale from on a scale of some value where the arithmetic mean is 0 and the standard deviation is 1. Okay, so that means the data will be displayed from -1 to 1. So now here we have got that. Let us just quickly save that into the X training information. And I'm going to call it as, this is going to be my noisy image, X train noisy. Okay, I hope this is clear. Okay, I hope this is clear. Now, so we have got the noisy data available, followed by you are going to get the noisy test set also, and which you will be using for testing purposes. So let's just include the noise factor again. We'll be having 50% noisy data in the testing set also, through which we will be testing our model. So let's again perform a normal distribution from location 0.0 up from locality or locale, which could be the mean. The mean value should be 0.0, along with the scale value will be 1.0, and the size of the data will be your x test dot shape. Okay, so here we are going to get x underscore text. So now what we have got, we have loaded MNIST dataset. We have introduced some noise with a noise factor of 50% along with a Gaussian normal distribution. Using this Gaussian normal random distribution using NumPy, we have got the noisy data as well as the noisy test set. Okay. So if you would like to see what comes in, once you do that, let's say we are going to check the test. Okay, so you're going to get the normal distribution data somewhat like this. I have just shown the test set to you. Okay, now what we are going to do, once we have got this information, we only would like to grab the test information for those cases which is between 0 to 1. Okay, we will not take that for the negative values. We're not going to take that for negative values. We'll be taking the values, we'll be clipping all the values from 0 to 1. Okay, so that will be our final noisy data. So let's just take that. I'm going to clip, so we can make use of the clip function here. What clip can do, clip can actually extract a number of information depending on the condition provided from an array. Okay, so let's say we have the X train noisy, and from this X train noisy, we will start the value from 0.0 to 1. Okay, and for float, you can also define somewhat like this, 0 point and 1 point. And whatever information you're going to grab, let's just save that into noisy. Okay, X train noisy will be clipping the information from the original noisy images from the value 0 to 1. Similarly, We'll grab the test set also. Let's just clip that x test noisy and grab that from 0 to 1 and just save that into x underscore test underscore noisy. Okay, and I'm going to show you how the noisy test set looks like. X test noise. Okay, so now you can see that we have clipped the information with values between 0 to 1. Okay, so now we have got the noisy data created. You would be asking why you have taken the values in positives only from 0 to 1, because just to let you all know, when we make use of autoencoders, these will be the actual values represented by the neurons, and neurons generally take the values from 0 to 1. Okay, so that's why we have clipped the values from 0 to 1. But why would have, in case if we have to take the value from 0 to 1, then we could have normalized the data. You would say why we have used the standard scaling process. We could have used any other normalization technique like min max scaling, which we can take and we can put the values between 0 to 1 only. So that could be done. But in general, the official definitions as per machine learning documentation says whenever you introduce any noise in any image or in any image kind of data available, that is generally done using Gaussian distribution. Okay, so when you do that with Gaussian distribution, you have to implement the Gaussian distribution formula, and you have to take the mean value as 0 and standard deviation as 1. That is the standard scaling formula. Okay, but now, so we have got the noisy data set ready. Now once we have got this noisy data set ready, let's just plot the noisy data. Plot the noisy data. Okay, so how you're going to do that? In order to plot the noisy data, again, we'll be taking the 10 characters like we have been doing it previously. Let's plot a figure. The figure size, the figure size, the figure size would be 40 cross 4. Let's say 40 cross 8, anything like that. You can take any image size as per your requirement. For I in range of n, for the n number of elements available in the range, we're going to make a subplot. Okay, so we'll start from 1, we'll go up to 1, we'll increment by I for every specific index. Okay, and I'm going to plot that. So just to make a plot, I'm going to make use of plot dot image show. I'm going to make use of x test noisy. I would like to get each image at the ith index. I'm going to reshape that image, and for display I would be reshaping it to 28 cross 28. And finally, I'm going to convert that into a gray scale image. A gray scale image. And once we're done, we're going to use plot.show. So let's run that. And we need to make use of matplot library, import matplotlib.pyplot as plt, and let's run it. And I'm getting number. Okay, now you can see we have got some dirty images here. Okay, can you see that? It's very difficult to observe. थोड़ा सा एक बार कम करके देखते हैं इसका नॉइज फैक्टर. लेट्स से 1% एक बार पहले करके देखते हैं. ठीक है, थोड़ी सी आई थिंक थोड़ी बेहतर हुई है, अब समझ में आ रहा है। फर्स्ट वाला 7 है, सेकंड वाला 2 है, बट सारे अभी भी समझ में यहाँ पे नहीं आ रहे, तो ठीक है, नॉइजी है डेटा हमारा। Okay, so I hope this is clear to all of you till now. But why I could have got with the ith value also, why the number of dimensions are not increasing? I have taken I range 40 cross 8 when I have got that. हाँ चलो ठीक है, तो एक ही आ जाएगा ना, ठीक है। Okay, now let's see. So please confirm me on chat how many of you have got, and let us just take a few images only. नहीं है, 40 क्रॉस 4 नहीं आ रही है, 20 क्रॉस 2 में देखना। ठीक है, चलिए, नॉट अ प्रॉब्लम। ओके, बना लीजिए आप लोग ये इमेजेस। बट मुझे 2 कॉलम्स अभी तो नहीं चाहिए ना, अभी तो हमारे पास एक ही है, ठीक है। 2 कॉलम्स का क्या करेंगे हम, 2 रोज का क्या करेंगे, सॉरी। So that is the number of rows, number of columns. ठीक है, आप लोग लिख लीजिए एक बार। Okay, so we have got certain dirty images. Are you all done till here? Please confirm me on chat. In case if you want to see any of the cells, just let me know. So we have started from here, applications of autoencoders, where we have started generation of noisy images. So we took the MNIST data set, we converted the image into a 3-dimensional image along with the channels information. Then we introduce a noise factor of 0.1 here. And using the noise factor, we have taken the random normalized scale up to 1. We took the training shape and the testing shape, information, training, noise factor. Then we took the X-test normal distributions. Okay, X-test noisy, X-test, we have got both of them, the normal distributions. We perform the clip information as well. We clipped the value of training noisy and testing noisy. Save that into training and testing noisy. We got to see the test, as well as we have got the figure plotted here. Okay, for some n number of characters. Okay, so I've got a message. Okay, done. Everybody is done. Let's go for it. So now what is the objective? So you know autoencoding. In an autoencoder, what generally we do, we have to use a convolutional autoencoder, as you all know. For convolutional autoencoder, you all remember that we make use of convolutional 2D classes in order to generate our hidden layers with the n number of neurons which we have to create in each layer, along with the weight matrix which will be applied to the inputs, and we are going to get the activation functions using rectified linear units. We are going to get certain layers. Using that layers, we are going to perform downsampling. Then we are going to create another layer. Then we are going to perform downsampling. Then we are going to create another layer. We are going to upsample. Then again, we are going to create another layer, followed by upsampling. And finally, we are going to decode with the sigmoid activation. Once we are done with that, we are going to make a model and binary cross entropy loss. And finally, we are going to train the model. And after training the model, we are going to predict and plot. Okay. So that's what we need to do. So now let's get started with the prediction. Not the prediction. Let's just perform convolutional image denoising. Noising using convolutional autoencoders. Okay, that's what we are going to do. So let's get started with the input layers. Now you all are clear that how do we get started with the inputs. Let's just import from keras.layers import convolutional 2D max pooling 2D upsampling 2D. We also need input and dense. We need input. Okay. And from keras dot models, we are going to import model, and then we're going to get started with the shape. So now once we get started with the shape, we are going to get a 3D image, which we have to provide to convolutional neural network. Okay, so that's going to be our input layer, and we are going to call it as input image. What happened? Input image. Okay, so we got a 3D image. Now what we are going to do, we're going to perform convolutional 2D. Let's make our first fully connected dense layer using convolutional 2D. So we don't use dense here actually, because dense, as you already know, we have been using that in the basic autoencoders. But once we have to implement convolutional autoencoder, then we need to use the class convolutional 2D only. Okay, so let's go for it. We are going to create 32 features. As you all remember in the previous session where we had the clean images, we have only used 16 neurons here. But since the images are denoised, so we would like to have some more features from the images so that we would be able to predict the images appropriately. Okay, so for that, we will be using some more number of neurons in the layer. So I'll be having 32 neurons in my first layer, let's say. And then I'm going to make use of 3,3. Okay. And this is going to be our kernel, the weight matrix, followed by the activation function. Okay. So activation. Oh, yeah. Okay. The activation will be rectified linear units, followed by we'll be having the padding. The padding will be same, followed by we are going to make use of the input image. Okay, input underscore image. We're going to make use of that. So we have made a convolutional 2D with 32 neurons with 3x3 weight matrix with activation function rectified linear unit with padding same, followed by the input image. And now we are going to save that into an image known as X. Now let's downsample it using max pooling 2D. Okay, using max pooling 2D, you're going to make it half. So when you downsample, you're going to pass a matrix. 2x2 will actually make half out of the original 32 neurons available, 32 features available. So let's use the same padding, and we're going to have a product with X. So we are going to save that again into X. So this is our first downsampled image. Again, I'm going to introduce one more layer, convolutional 2D. Okay. So once I'm not deducing the features. I would like to activate the same number of features again, because in this case, the input images were the denoised images with the noisy images. Okay. So I would like to reconfirm when from 784 features from the input layer, when 784 features from the input layer, when we generated the 32 neurons in the hidden layer, we again would like to activate the same number of neurons in the next layer. You can actually reduce the number of features and increase the number of features also. That won't be a problem. But having the same number of neurons would actually help you activate the appropriate features. Okay, so sometimes you can use it that way. Moreover, you can try with different number of layers and you can see minor differences in the results. Okay, so we are going to have a weight matrix of 3 cross 3. Along with that, we're going to have an activation function that will be our rectified linear unit, followed by the padding, which is going to be the same padding, as well as we would like to put the values into X, and let me store that into X. So I've got that. Finally, again, I'm going to downsample it. So for downsampling, I'll be using max pooling 2D. Again, I'm going to make a half of the current information available so that my images become 7 cross 7 comma 32. Okay. And so what we are going to do, we are going to make use of padding. And once we perform padding, we're going to define the same value X. And with the max pooling 2D, I would like to keep that into the encoded features. Okay. So we got the encoder ready. Now let's get started with the decoder function. So once you guys are done with the encoding, okay, now what you need to do, you need to work out on the decoder now. So again, let's decode from the encoded images. Let's make use of convolutional 2D. Let's make 32 features. Let's make out 3 comma 3. Okay, we'll be having an activation function. This activation function will be rectified linear unit. Again, you will be having padding. We'll be having same padding, followed by we'll be having the encoded data. Okay. So we are going to use the encoded data and we are going to save that again into X. Now we are decoding from the encoded layer. You have to perform upsampling. Once you perform upsampling 2D, you're going to double the size of the information, double the size of the matrix. And again, let's save that into X. So this we generally do in order to learn more and more features available in the input data. Okay, so that we can actually identify the similar images. Followed by, again, we are going to make use of 32 neurons in the layer because similar kind of architecture we have designed in the encoder. Now we are going to make use of an activation function, which is again rectified linear unit. Okay. And once we have performed the activation, we are going to provide the padding. Let's keep the padding information. The padding will be same. And I'm going to have a product with X. So in the upsampling, I would like to save it into X, line number 14. Again, we need to downsample it. We have to upsample it. So once you upsample it, again, you have to use upsampling. Use upsampling 2D, double it. Okay. Once you're done with doubling, have a product with X and you get the X. Upsampling 2D, we have generated the double matrix out of it. Save that into X. Okay. Now finally, we are going to generate the decoded layer, convolutional 2D, and this time once finally we will be generating, so we'll be having one neuron out of it because we have to work out on the specific character, as well as we have got a 3 cross 3 weight matrix. I'm going to have an activation function. This activation function is going to be a sigmoid activation function. You're going to define the padding. Once you define the padding, finally have a product with X and save that into decoder. So now what you have got the encoder as well as the decoder. So let's create the model. So let's just first run it and see in case if there is any trouble. Okay, so I've got activate on, I have written somewhere on line number 147 on line number 13. Line number 13, I have got activate on. Okay, activation. Okay, now, so we got our image denoising convolutional autoencoder ready with encoder and decoder layers. Now let's just make the autoencoder. So to make the autoencoder, we are going to make use of the input image as well as the decoded image, which we have received. And we are going to save that model into, let's say, an autoencoder model, input and decoded. Let's just compile autoencoder.compile. You have to compile with the optimizer. Let's say your optimizer will be ADA delta, and your loss will be binary cross entropy. Okay. So we have got the compilation process as well. So let's run it. Let's run the cell. So we got the model ready. Now we are going to train the image denoising model. For training, we are going to make use of autoencoder.fit. I'm going to define my training data as xtraining, noisy. Okay. For learning features, I'm going to define the original information, xtraining, which was given. Because now this time you need to understand we are providing the noisy data and we are giving the original data of the training also, which we have generated at the top as the labels, as the Y information. So now this becomes just a kind of classification where we are providing him the labeled images as well. We are saying that X information, the independent variables which are here, these independent variables will be the noisy images. And it is available on these dependent variables. We have to classify out of the data available in the image itself, in the original data set. So here there is a kind of mapping we are doing. We are implementing the classification kind of scenario here, where we have the noisy data, but out of that noisy data, we will be actually classifying the images actually available in the original training data. Okay. So I hope this is clear. Now, once we have defined that information in the X and Y, what next we're going to do? We're going to define the number of iterations. Let's say the number of iterations will be 100. Batch size, you can define for parallel processing. Let's say the batch size will be 128, followed by shuffling is true. And I would like to have the validation data. And the validation data will be my noisy data, X test with a noisy, and the original testing data. So for validations, what we will be doing, we'll be taking independent test variables as X test noisy and dependent text variables as X test. Okay. So we got that. Let's just fit the model. Okay. So we started prediction on layer number 1. You can see that on first number of iterations for 60,000 samples, we are getting a loss on the training data is 0.30, which means we would be expecting some fine results. Okay. So all of you, those who are running the test, just confirm me if you guys are running the test. In case if anybody wants to see any of the code which we have implemented till now, let me know. I'll show you that. So just I'll give you a quick brief again. We have started working on applications of autoencoders, and the application is image denoising. So we took the data set, we introduced some noise into it, Using the noise, we have generated some noisy data, somewhat like this. Now, out of this noisy data, we would like to denoise the data. So, what we have done, we have taken the inputs of the noisy data and we are trying to classify the denoised information, and we are training our autoencoder to learn the features of noisy data which resembles with the features of original data in the training. And depending on that, we have got a model that is an autoencoder model. And using that, we will be performing prediction. Okay, so let's see what do we get. Okay, so you all have reached till here. Just let me know on chat. Okay, for the time being, till my till my training. Okay, everyone. So there is one more information which you all can add up. Whenever you are training and your reposes are slow, by default, the runtime is in the runtime is not accelerated by a hardware. So there is an option in the Jupyter Google Colab which you can implement. You can go to runtime. Under the runtime, sorry, you can go to edit. Under the edit, there is netbook settings, notebook settings. Under notebook settings, what you can do is there are hardware accelerator options. By default, the hardware accelerator is set to none. So you can change to GPUs and TPUs. And what it can do, it can help you run your code faster. Okay. So once you select the GPU, you can see that you've got the images processed better. I have taken the factor as 0.5 here with some 50% noise introduced in the images, followed by, now we are training the data. So I've got approximately 33 epochs done. And as soon as we are done with 100 number of iterations, we will get some improved results. Okay, I hope the concept is clear to all of you, that we have got certain images, we have generated noisy images, and now using those noisy images, we are going to denoise the images and we are going to identify the actual images out of the noisy one. So these are the concepts where we apply compression, decompression, dimensionality reduction, which are quite important. And you will be implementing a lot more nice artificial intelligence, machine learning features as soon as you progress further. Okay, so guys, now we are done. And as you all can see, we have got a value loss of 0.0937. So this seems to be a better output which we have got, 0.09, that is the loss over the testing data. And we have got a similar loss value on the training data. So let's now go for the next cell and we are going to implement the plot. So finally, let's predict the images after denoising. Okay. So now what we are going to do, we are going to make use of the prediction. So we'll use autoencoder. We're going to predict the model depending on the X test noisy. We are going to take the noisy data set and we are going to take the decoded images. Okay. So we'll be taking the noisy data set as the input and we'll be predicting the decoded images. For that, let's just go for n number of samples. Let's just make a figure, plt.figure. You are going to make use of a figure size again of around 20 cross 4, whatever we have taken at the top. Then for I in range of n, we are going to define the subplot. For the subplot, we'll have two rows, a number of columns, and the ith value, followed by we're going to show, plot.image_show. Using the image show, we are going to have our noisy images, X test noisy of I. You're going to reshape that images. Let's put in 28 cross 28, and we are going to make a gray plot. Then we are going to plot our next subplot, which is again going to be two rows, n columns with values greater than I plus n. We're going to perform plot.image_show. We're going to make use of decoded images and the decoded images at ith index. And we're going to make use of reshape. Now for reshape, we'll be taking 28 cross 28 and we're going to make a gray plot. And finally, we're going to show the plot. Okay. So let's run that. Let's see what we get. So it says, okay, number is greater than as is other than 20, I plus 1. Okay. So just skip the first image. Okay, because somehow it's taking some problems at the 0. So you can consider your input set from here. Okay. And the same input set, we are getting an output for that image here. Okay. So here this is 2, this is 1, this is 0, this is 4, this is 1, again this is 4, this is 9, this is 5, and 9 again. Okay. So now, similarly, now you can see that you have got the denoised data set, but out of the denoised data set, you are actually getting the appropriate output of the images predicted in the actual way as available in MNIST. So this is one such application of autoencoding where you can denoise the images. So the objective was, we have got certain images and there was a noise in the backend. Now, once these noise have been removed, we have actually got the appropriate images. Okay. So here, now you can see there is no noise and we have appropriately got the features. I hope this is clear to everyone. Have you all understood the concepts of what is autoencoding and how you can actually implement autoencoders in order to perform different applications? Okay. In case if you would like to see any code here, you all can quickly see that and test it. And once done, let me know on chat. Okay, so we got below set done. Okay, so there is one more. Do you know how to use the TPUs? I tried using them, but they are slower than regular CPU processing. So yeah, you can simply use the TPUs by going to changing the runtime type also. Okay, so what you can do is you can change the runtime type, and then you have to perform certain optimizations. You can select the TPU. Both ways you can configure that. So initially, once you're done with configuration or selection, you can select the tensor processing unit. But once you will be writing the code, then you have to make sure that your TPU devices are properly recognized by the Jupyter environment where you are running your code. So for that, what you generally need to do, you need to identify the appropriate collab tensor processing unit address. So there are certain ways available in os.environment which you can make use of, and then you can make use of a class known as session. So what you can do is you can define something like this. Let me just show that to you. Generally, when we use TensorFlow, we make use of TensorFlow. Then we define the session, and within this session, you have to appropriately define the tensor processing unit address. So once you set that tensor processing unit, appropriate tensor processing unit with your current tensor object, then it will be able to perform the processing faster. Okay. So that's actually very simple. You can actually grab the information out of the available tensor. So I can give you a quick information to that as well. Let me just go for it. Okay, so for now, just confirm me if you all are done with configuration of your if you all are done with configuration of your denoising. Then there is one more hardware acceleration also, that is TPU hardware acceleration. But TPU hardware acceleration will work with TensorFlow when you will be actually able to identify the appropriate TensorFlow addresses available in the collaboratory, and then you have to set those addresses. Okay. So just to quickly give you how you can identify the addresses, you can make use of a few information. We can use pprint to quickly define the information. Along with that, let's just make use of TensorFlow as well as TF. Okay. So we got to make use of these three libraries in order to appropriately perform. Okay. So there is one way to identify the address of TPU. So what you can do is you can actually either you can search in the OS environment. Okay. In case if you are not connected to the TPU runtime, so that's actually very easy. You can make use of gRPC protocol in order to identify that. So generally what gRPC protocol can do, it can actually access the cloud and can give you the information from OS environments. Let's say I'm going to use OS environments, and within that there is a collab TPU address stored there. So you can actually extract that information, and then you can store that somewhere into, let's say, a TPU address. So if you got the appropriate TPU address, then what you can do is you can set the TPU address. Okay. So let's say I'm going to define a simple TPU address, and you can define the TPU address here. So the current TPU address is working on gRPC 10.64.52.8470. Okay. Now, in case if you want to connect that with tensor processing, where is the next cell? Okay. Now what you can do is you can make use of your tensor session. So let's say you can use TensorFlow session, tf.session. You can define your TPU address. Okay. And then you can define, let's say, in case if you would like to see a list of the devices, let's say I will be taking it as session. And what you can do is, in case, let's say we're going to write that with session, that would be better. Session, and this session will give you a list of devices which are actually available over here. let's say it will be list devices, I believe, list devices, and let me just throw that here into the devices. And let's just finally, once we got the devices, let's just print the devices. And devices. Okay. TF dot session. Actually, we do have the TF dot session. I just need to check why they don't have that. Okay, maybe they would have changed the name of that class. Maybe what I'll do is I'll just check with the appropriate session class which they have. TensorFlow session not found. Okay, I'll just check back with them. I think the session variable would have been changed here. Okay, so for that, generally what we do is we just set the session with that specific value, and then we see what all devices are available and you can connect your process. But here I think they have changed the session class. So I'll just check that and we'll get back to you that how you can quickly do that. Okay. Okay, so we can use that with V version. Okay, so this is version 2 actually. So this was available with version 1. So I'll just check in case if I have access to version 1, or else I can set the TensorFlow as version 1. TF dot, yeah, TensorFlow as TF stack. TF dot compat dot v1 dot session 1. Okay. TF dot compatibility dot v1 dot session. Yeah, here. So these are the following device attributes which are available. So let's say these are the specific devices which are actually running your tensor network, TensorFlow devices. Okay. So once you have got that, you can make use of the optimizer similarly by using the TPU estimator specifications, that you can define the model and then you can run that in order to read the performance gains. So we'll be taking up one detailed session on how you can make use of these estimators. So one more thing which you need to do is you just need to make use of TPU estimator specification, and you have to provide your training, your prediction information, your loss information, and then it will process and perform the appropriate output for you. Okay. So we'll be having some sessions on TPU so that you all will get to know much more information about it. So I hope this is clear. Below, you can make use of TensorFlow by identifying the appropriate tensor device, and then you can set it as a session and you can actually run that. So by just selecting the TensorFlow, runtime won't work. Just you need to identify the appropriate device and set the session and then execute your models. Now, what next we have? So we are done with this concept of image denoising. Everybody is clear with image denoising? Please confirm me on chat if you all are done with the concepts of image denoising. And have you understood that? That is more important. So, okay, I can see Vinay sir and Anshu Dhawan. I think Astha Tyagi is not available here. Not a problem. Okay, great. Okay, so let's go for the next one. So once you have got the denoised images, now you have to work out on something very, very important, and that is variational autoencoders. Okay. So this is something which is very, very important when it comes to designing the concepts. Okay. So for that, let me just quickly explain you what variational autoencoders are. And today I have some assignments for you. First of all, what you have to go through is Variational autoencoders are very important, and the math behind it is also very important. So first of all, what I want you all to do is you all need to understand what is a variational autoencoder from this one of the finest articles on autoencoders available from Stanford University. So I'm going to share this information with you from here, the variational autoencoders, and share at this time. Copy and share. Okay, I'll just put that on Trello on all your devices. Let's go here. Okay. So today, what next you need to do? First of all, you need to understand fundamentals of variational autoencoders and generative adversarial networks. We call them as GANs. Okay, and this concept is very, very important. So you can consider it as your most important stage of machine learning, as well as this is also known as the final stage of machine learning, where we work on generative adversarial networks. Okay, we generate GANs. So before I land up to explaining what variational autoencoders are and what GANs are, I just want you all today to go through with this very nice video session. You will understand uh, all the theoretical concept behind running of a variational autoencoder, as well as the generative adversarial networks. You all have to go through with this. A very nice, one of the very finest tutorials available. So, but that is the conceptual implementation of autoencoders. You will be able to understand all the concepts behind it. But before I proceed to convolutional autoencoders, I would like to show you what variational autoencoders are actually capable of doing. So I will show you some examples. There is a website, this person does not exist. Okay. So I would like to share a link to all of you to this website. Kindly open this website. Okay. This person does not exist.com. Okay, sorry, I've got your Google one. This person does not exist.com. Okay, open this URL. This person does not exist. So this is one of the finest examples of generative adversarial networks, as well as you can also consider it as a variational autoencoder example also. So this is imagined by generative adversarial networks. Now what is displayed to you here? You all will be amazed to see the photographs which are coming here. These persons does not exist. So this face, which you are actually seeing on the screen as of now, this person does not exist in the world. These images are randomly generated by artificial intelligence, by generative adversarial networks, or you can also consider them as variational autoencoders. So this is quite strange that how machines are capable of generating real type of faces, eyes, ears, and everything like that, just like the God does. Okay. So can you all imagine the faces which are appearing in front of you? They are not real images, and they are computer generated images. They are computer generated faces actually. Okay, so you might be thinking how computer is so smart that he is able to create human faces in such a nice way. So I would be glad to tell you it's not just about faces. Computers, using the concepts of autoencoders, variational autoencoders, using the concepts of generative adversarial networks, today are able to create paintings, they are able to create music, they are able to create any creative stuff available out in the world. Okay, so now what you have to do is you need to understand these concepts, that with a combination of n number of images given to the inputs. Okay, out of those inputs, out of the inputs of various features learned, like the features of hair, the features of eyes, the features of skin color, the features of lips, the features of eyebrows, and all of these are actually trained. The neural networks learned all these features of n number of people available, or n number of faces available in the data set, and out of that it identified n number of features and generated new images. Okay, so consider an example. I'm in search of a beautiful face where I should stop and then I should uh, continue my uh, uh, chalo better. Okay, let's see. So now I'll explain here. Here. So suppose you have an input image. I'll type on the left hand side. Let's say you have, okay, that does not look good. Let's just put a red color here. Okay. Suppose, so you have an input image. Okay. What you're going to do, you're going to put that input image into a variational autoencoder, or else you can say a generative adversarial networks. And what that network is capable of, it can generate new images. Okay, the images which are actually not available in the data set. So this is the power of variational autoencoders and generative adversarial networks. Okay, are you all understanding what is a variational autoencoder? So we have got, let's say we have got certain inputs. Using those inputs, we are not only going to predict the similar kind of stuff, we can even generate the samples. We can generate new images available through using the inputs available. So that's what variational autoencoders is. So what it actually does, what is the significance of variational autoencoder? What we will see it somewhat like this. Given an image, or else an input. It could be any input, it could be art, it could be music, it could be paintings, any information you can give. Given an image input, process through VAE, and VAE will generate variations in images. Okay, variations in images, as in, let's say I have given a character, let's say 7. Okay, so now if I have given 7, now what VAE will be capable of doing, VAE will be able to generate n number of 7 kind of images to me. It could be a 7 like this, it could be a 7 like this, it could be a simple 7 like this, it could be a 7 like this. Okay, kind of that. So n number of variations can be generated using a variational autoencoder. So what will happen, we are going to give one input image, and how many variations, with what many variations we can represent 7 can be generated using a variational autoencoder. So this is just a random example of variational autoencoder. This is an example of generative adversarial network, which sooner you all will be going to generate stuff like that. Okay, but for now I would like to take you to the MNIST example so that you all can relate to the existing documentations and references, and then you can use this concepts and knowledge with your specific projects. Now, so I would like to show you variational autoencoders, variational autoencoder examples in the images. Okay, so now I would like to show you, I have got certain very nice examples though, which I would like to show. Not here, not here, not here. I would like to show you one very nice example, which would be like very good for you all to understand. Okay, I would be having that in my card. So let me just show you. Let me grab that. Where was that? I have used that for references somewhere. Comprehensive reparameterization, autoencoder VAE. Let me just test that. No, not this one. Just give me a moment. I'm just showing you one of the finest article which can give you a quick understanding of what exactly it is. I've got this technical explanation, VA image, VA variation autoencoder, explaining with code. Let's say this. No, not this. Reparameterization technique, maybe this comprehensive introduction. Not this. Mm-mm. Not this one. Not even this. Mm. I think I missed the image, but it was like a very fine article which I have read on. Just give me a moment. I would like to show you that. Variational autoencoder, weights 1 and weights 2. I have seen it where maybe. Okay, guys, just give me a moment. Let me just grab that resource for you. Somehow I forgot to keep a note of that, but it was like one of the finest which I have actually read. Animation VAs. Which article is this? I think it's animated VAE. Not this one. No, not this one. Conditional towards data science. Okay, I don't know. Somehow I referred so many articles in this, but let me just quickly grab that. I would be having it somewhere here. Maybe here. Explanations. Let me just close the previous ones first. So I think you have got this lecture 13. You all have to view this lecture 13. This is a very nice article which you all have to go through. And by the time I'm looking for one other article which I have seen, just I have to show you an image over there which could give you a complete appropriate understanding of what kind of variations could be generated. uh, just show you. Somehow, I guess I missed that image, and I'm very sorry that I missed that image. It was a very nice image which I have thought of showing you. Shit. But never mind, I'll definitely find it. This is, I think we have understood yesterday. Okay, so let me just try a quick Google search. Head pose variational autoencoder. Okay, yeah, I think this could be an example, but that's not the example which I was actually looking for. But here we have two examples which are similar to variations, which I was planning to explain. Here also we do have some examples here for variational image generations. Okay. Uh, let me just get back. ओके हियर सो अब आप लोग देख सकते हैं यहाँ पे जैसे मैंने आपके सामने कुछ इमेजेस जनरेट किए हैं मतलब मैंने जनरेट नहीं किए यहाँ पे हमने ढूंढे हैं ओके चलिए कोई नहीं मैं इसी इमेज में से आपको एक्सप्लेन करने की कोशिश करता हूँ अगर आप ये जो करंट इमेज जो आपके सामने खुला हुआ है अगर आप इसको देखेंगे ठीक है सो मान लीजिए आपके पास एक इनपुट इमेज है ठीक है ये इनपुट इमेज फ्रंट साइड ऑफ द यूजर है ओके इसी के साथ में अगर आप देखेंगे तो यहाँ पे एक इमेज है जो कि टोटली टिल्टेड टुवर्ड्स लेफ्ट है ओके ये पूरा एक मिनिमम रेंज है, यहाँ से लेके अगर आप एंड तक देखेंगे ये सारी इमेजेस लेफ्ट टिल्टेड है, और अगर आप बॉटम में देखेंगे तो सारी इमेजेस राइट टिल्टेड है, ठीक है। अगर आप टॉप से बॉटम देखते हैं तो देयर आर सर्टेन वेरिएशंस। यहाँ पे एक वेरिएशन है, वी कैन कॉल इट एज वेरिएशन 1, वेरिएशन 1, so this is variation along rows, okay, you can call it as variation along x or variation along rows, कि हर रो में कुछ नंबर ऑफ वेरिएशंस हैं। सिमिलरली हमारे पास यहाँ पे है वेरिएशन विथ रेस्पेक्ट टू लेट्स से y, यहाँ पे कॉलम्स की मैं बात कर रहा हूँ, टॉप से बॉटम आप लोग चेक करेंगे, ठीक है। सो अगर आप यहाँ पे अगर बात करते हैं, जैसे मैं एक x रो की बात करता हूँ, तो x में अगर आप देखेंगे तो द पर्सन इज ट्राइंग टू स्माइल इन दिस रेंज, ओके। इसमें ये थोड़ा सा स्माइल करने की कोशिश कर रहा है। यहाँ पे उसके पास सर्टन इमेजेस हैं कि फ्रंट फेस है, और फ्रंट फेस की स्माइलिंग के कुछ अलग अलग सैम्पल्स हैं, 7 सैम्पल्स हैं, ठीक है। तो यहाँ पे अगर आप देखेंगे तो वेरिएशंस हो रहे हैं उसके स्माइल में। सिमिलरली यहाँ पे आपके पास जब आप कॉलम वाइज देखते हैं तो कुछ वेरिएशंस हैं यूजर के फ्रॉम लेफ्ट हैंड साइड टू राइट हैंड साइड। अब इन दोनों का x और y का अगर हम कॉम्बिनेशन ऑफ प्रोडक्ट लें तो हमारे पास ये सारे के सारे सैंपल्स जनरेट हो जाएंगे, ओके। कि यूजर एक लेफ्ट हैंड साइड की तरफ फेस करने से लेके जितने भी नंबर ऑफ उसके वेरिएशंस हो सकते हैं टोटल राइट साइड में टिल्ट करने के लिए, वो पूरे के पूरे वेरिएशंस हम वेरिएशनल ऑटो एनकोडर से हम जनरेट कर सकते हैं, ओके। सो ऑल दीज कैन बी जनरेटेड यूजिंग अ VAE. So what could variation autoencoder can do? Given an image, using that image, variational autoencoder can create n number of variations possible and it can generate new samples. So अब अगर आपके सामने देखेंगे तो यहाँ पे आपके पास दो चीजें हैं। ये आपका इनपुट है, इनपुट टेकन टू वेरिएशनल autoencoder, and it has generated n number of samples with n number of variations for you. This is something a variational autoencoder can do for you. Is that clear? समझ पा रहे हैं आप वेरिएशनल ऑटोएनकोडर क्या है? अभी तक हम ऑटोएनकोडर्स के थ्रू इनपुट इमेज को रिकंस्ट्रक्ट करते हुए आए हैं, बट वेरिएशनल ऑटोएनकोडर रिकंस्ट्रक्ट तो करेगा इमेज को, बट विथ सम वेरिएशंस, ओके। सो इनपुट इज नॉट गोइंग टू बी इक्वल टू द आउटपुट. We will take the input, but output are going to be different samples which will be created, and these samples will have some variations depending on some variation functions which we will define in our kernel matrices in the encoders, so that generative images can be generated with variations in it. I hope you all are understanding my point, what exactly variational autoencoder is. Variational autoencoder is a kind of autoencoding technique where you can give a sample and it can generate various samples, okay. You can regenerate various images using that autoencoder. I hope you all are clear with what could be variational autoencoder. So we will be working in details in variational autoencoders and post variational autoencoders. The final thing which you guys will be using is the generative adversarial networks, which can generate new samples for you, okay. So that's what the power of machine learning today. Given an input, you can generate new samples, and here we do have n number of examples available over here. Let's say there is another example of the women available over here. Let me just open the paper and see what they are talking about in this variational autoencoder. So you can see that there are different types of images available for people. So n number of photos for a lady is there, for n number of faces, and right from, let's say a given input is somewhat like this, okay, but n number of variations can be generated with it. So she had one photograph with specs on, but now you can see that with the specs there are so many images can be generated. Specs with a tilted head, with some dark shades of specs, kind of that, okay. So this is the power of variational autoencoders, which can actually generate variations depending on the input given. But we will be working on generative adversarial networks, and what generative adversarial networks are capable of. You can see GAN can even generate music. Okay. So generative adversarial networks, paintings. Okay, you can see a lot of examples. So here you can see that uh, you can see that this is the first painting created by artificial intelligence, sold for $432,500. Okay, so this is the painting by artificial intelligence at sold at Christie's at $432,500, and this image was the first image generated by artificial intelligence. So it took n number of features and it actually generated the images. Okay. So apart from this, I would like to show you n number of images which have been available over here. So you all can see these are the paintings which are being generated by generative adversarial networks by learning samples of images. So you can see that. Can you see that? Are you all able to understand what are the possibilities of neural networks? So the possibilities of neural networks are somewhat like this. So we have already seen this. This person does not exist. Along with that, there are so many options which you will be glad to explore. And I would like to share this article with you. GAN from zero to hero. I think this article you all can refer, where there are various examples of images, and these are the person images which I've already shown you. I've shown you this article. Apart from that, variations of, in our example, what we will be doing, we will be generating variations of the characters. Okay. So let's say if we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many different ways we can represent a specific number? So using that example of MNIST, you will be able to implement generative adversarial networks. Depending on, you can see that various Jim Carrey face has been generated using the neural network. So neural network has generated this Jim Carrey face. Along with that, there are so many other options. Okay. These are some of the real inspirational examples which have been generated using generative adversarial networks. Along with these are also the images created by creating the images of horses, sofa, bus, automobile, cycles, a lot of things neural network was capable of learning and it generated. So you can see that approximately all kinds of devices and elements and items which you encounter daily, all these can be generated using neural networks. Okay. Similarly, here there are certain dance kind of images. From horse, the zebra has been generated. You can see that. Okay, so this is the animated portrait. Similarly, various cartoon characters out of different images given as input have been generated. So you can see that all these things can be done. So all these things are automated. So the creativity which was earlier, which was very difficult. So now you can see that somebody could, let's say, draw a simple example, and using the artificial intelligence, an appropriate image can be generated. Okay. So, artificial intelligence is making a lot of things a reality, which used to be a science fiction in, let's say, 5 years back. But now artificial intelligence is creating all these things with ease. And I hope if you all are able to understand the concepts well, you all will be able to produce output like these. So that's all for the day, where you understood a lot about autoencoders. So I would recommend you to go through with these concepts again. We have taken these concepts in sequence just to make you understand each and every step, that how things are working. and how you can implement all those things in practical, how you can define your own code, how you can make use of uh, existing frameworks, and then how will you be using these technologies in applications. And finally, you will be working towards generative adversarial networks and variational autoencoders. So if anybody has any questions, please ask me. Otherwise, we are good to go, and we'll be meeting on next session on Saturday, and we'll work with advanced concepts on neural networks. Any questions, anyone? Okay, so I hope there is no question. Later, you guys can post your questions on Trello in case if you get any. So that's all for